Welcome back again to MPVAT Live Lessons, whether you're watching this on a recording or live right now. Tonight we are doing Chemistry Paper 1. Now before we start, we are going to just say that each tier and group, for example, combined, triple, foundation or higher tier, will have content relevant to them. But the good thing for chemistry is there are several overlaps. For some reason, not much of the topics have been taken out compared to other sciences, but it'll just be in the bottom right just in case. First, we will start with an overview of 5 topics with some allocated time I plan to spend. First, we start with atomic structure in the periodic table, some of which is a crossover with physics. And an overview of the units involves atomic structure, elements, compounds and mixtures, the periodic table in its history, as well as some group properties. First is the atomic structure. So we start with an exam question. Describe the atomic structure of an atom of carbon-12. You may draw a diagram to support your answer, 4 marks. And just a reminder, you have 3 subatomic particles, the proton, neutron, and electron. And remember, for charges, we put the number, then the polarity, if it's positive or negative, and the mass just after as well, just 1 or 0. Now we'll go over this answer here. So on the periodic table, you'll see the carbon atom or element described as like a C, and then a number on top saying 12, and then a number on the bottom saying 6. For the number on the bottom is the atomic number, tells us how many protons there are. So the first mark is that there are 6 protons. Now the mass number tells us the number of protons and neutrons. We ignore the number of electrons because they have no mass. Therefore, there are 6 neutrons. Since we know the overall charge of an atom is 0, we must have the same number of protons and electrons because their charges are opposite and cancel each other out. So therefore there's 6 electrons. But that's not it. The 6 electrons are arranged in a specific way. If you remember, we have shells. So 2 electrons in the first shell and 4 electrons in the second shell. We'll come to that later. Next we have electronic structure. So this is how the electrons are arranged in these shells. So first, electrons are filled, starting with the first shell, then the next, if it becomes full. For example, 16 electrons in the oxygen atom are filled like this. First, there's 2 in the first shell, because you can have a maximum of 2 here. In the second shell, you can have a maximum of 8. So 8 are put here. We've filled in 10 electrons so far. And finally, we need 6 more electrons, and in the third shell, it can have a maximum of 8. So we've got 16 electrons, so 2 in the first, 8 in the second, 6 in the third shell. This is called electronic configuration, and it can be drawn out or written in brackets like this. 2, 8, 6. First shell, second shell, and then the third shell. A little diagram might be shown as well. And remember to show electrons as an X or a dot. Next we come onto the model of the atom. Now this is often a high mark question where you'll need to know quite a lot about this. You may need to explain how it developed over the years. Now a model is a way to explain properties of an atom. And these models can change because of experiments. And the model changes because the new evidence doesn't support the older model, so it doesn't make sense anymore, I feel like. So at first, the Greeks thought substances were made up of atoms, which were very small spheres that couldn't be divided up further. This stayed the same until J.J. Thomson in the 1900s discovered the electron, a negatively charged particle. Now, at that time, they didn't know the atom's overall charge was neutral. They didn't know about the nucleus either. And therefore, J.J. Thomson created what you know as the plum pudding model. So this explained the overall neutral charge, where there were negatively charged electrons were stuck onto a larger sphere of positive charge, or embedded, is another word. And overall, you could be asked to draw the plum pudding model. So you draw a big sphere. You can denote this with a plus sign to show it's a positive charge, and then put little electrons on the outside like this. Now, this scientist, J.J. Thomson, had some students called Rutherford, Geiger, and Marsden. They carried out the alpha scattering experiment in 1909, not long after. Now, alpha particles are positively charged. In fact, they're a helium nucleus, and if you look on the periodic table, they have 2 protons, so they have a charge of 2 plus. Now, they were fired at a thin sheet of gold, and their results were conflicting to the plum pudding model. What they found as a result of this investigation was the atom is mostly empty space, the atom has a concentrated positive charge, and a concentrated mass in the nucleus. Here is a diagram showing what would have expected to happen versus what actually happened. So, as expected, when the alpha particles were shot through the positive sphere of the plum pudding model, it would expected to deflect slightly because light charges repel. However, what happened was some of the alpha particles went straight through as if they weren't affected by anything, some were deflected more than expected, and some were even sent back, so that meant at the center there was a nucleus of positive charge. And since these alpha particles may have got close to this nucleus, they would have been repelled even more. That's why it repelled further than expected or even sent back. And from then on, this nuclear model, hence the nucleus, was changed further or adapted. So Niels Bohr found that electrons were organized in shells. This was through a bit of maths or calculations, which you don't need to know as well. And James Chadwick found the existence of neutrons. These are the same mass as protons, but with no charge, and this explained the same element with different masses, so isotopes. For example, you could have a carbon atom. They'll still both have 6 protons, but they may have different numbers of neutrons. They can have therefore different masses. You could have carbon-12 and carbon-13. These are isotopes. Now we move on to the history of the periodic table. Some context. This was in the 1870s within Russia or Europe. Now Mendeleev made the periodic table well before any subatomic particles were discovered. This was well before any electron was discovered, any of the protons, neutrons, electrons. So only they knew the mass number or atomic weight of the atoms were known. Now, atomic weight is actually different from the mass number because this is based off a natural sample. And then at a natural sample, you can have different isotopes or different abundances of each isotope. For example, chlorine, a natural sample of chlorine, could contain different isotopes, namely chlorine 35 and chlorine 37. So therefore its actual mass is between those two, depending on how much there is of each. Now at that time, scientists tried ordering the elements in ascending order of their atomic rates. Some of them put them in octaves, 8 per row. The problem was, even though some elements matched with others in a column with similar properties, others didn't. What Mendeleev did was similar, but in a different way. He ordered the elements also by atomic weight, but did it differently. Firstly, he grouped elements that had similar properties strictly, like chlorine, bromine, and iodine, which you know are group 7. And the halogens. And to do that, he left blank spaces, and even boldly predicted elements that weren't discovered yet. When they were found, his predictions were also quite accurate. And this could be a common question. Another thing he did was he sometimes even switched the order of some elements. For example, if you look in the periodic table, you'll have this element Te, then iodine, and their mass numbers are reversed. Tellurium has 128 mass, and iodine has 127 mass, because iodine fits better into group 7 than tellurium. Next, we have elements, compounds, and mixtures. Now, I suggest you get these down onto flashcards, and you may see this flashcard icon in the top right reappear many times throughout this lesson. We need to learn a few definitions first. An element consists of one type of atom. This is the same number of protons, for example. For example, carbon atoms are an element, and they only consist of atoms that have 6 protons. Next, you'll need to know the definition of a compound. So these consist of multiple elements chemically bonded together. In the next units, you will see how these bond together. For example, you could have the compound H2O, which is water. So it'll have hydrogen atoms, 2 of them, bonded to 1 oxygen atom. Now remember, we write these numbers as subscripts, so below the letters slightly, to say how many of each there are. Molecules consist of multiple atoms chemically bonded together. So this could be an element or a compound. For example, a molecule of oxygen talks about 2 oxygen molecules bonded together. And finally, you'll need to know what a mixture is. This can consist of several substances. These can be elements, compounds, one of those, or in between. And these aren't chemically bonded together. A good example is salt and water, and you can tell it's a mixture usually because of separation techniques. 3 of which you need to know are filtration, crystallization, and distillation. Filtration removes insoluble solids from a solid, or like, let's say water. Crystallization removes a soluble solid. This is where you heat the substance up until all the liquid evaporates. And distillation involves removing a liquid. That can be either from another liquid, or it could also be from a solid. Now, for this unit, you'll need to know about some properties of metals. First, we'll start with group 1 metals. You'll need to know about what these atoms will have in common. So we'll have these common properties and the trends of them. Now, group 1 metals have 1 electron on their outer shell. Now, atoms want to become stable, as in they want to have a full outer shell of electrons. They can do this by gaining electrons or losing electrons. Group 1 metals tend to lose their single outer shell electron because gaining 7 needs more energy, which can't happen as much. So these will often lose its electron to become a 1 plus charge ion. You'll learn more about ions soon. These group 1 metals are also quite soft, meaning they're easy to cut, like with a scalpel. They form white powders with other elements, such as with group 7 elements in a compound. For example, sodium chloride is just your regular salt, which you know is just simply white. These can react vigorously with oxygen and acids. These also react with water, produce an alkali compound. So that's why these group 1 metals are called the alkaline metals. Now, as you go down the group, the melting point increases and they become more reactive as you go down the group. And you'll see why soon. Next, with group 7 are the halogens. Now, you also see their common properties and trends. They have 7 electrons in their outer shell, which is just 1 electron away to make the full 8 and become stable. So they gain 1 electron to become a 1 minus charge ion. These are usually found as pairs of atoms in a molecule or diatomic molecules. Their boiling point increases as you go down the group. Their reactivity decrease as you go down the group. And then more reactive halogens can displace less reactive ones in the compound. For example, as you know, the reactivity of these group 7 elements decrease. So if I write down the order of them, which is fluorine, chlorine, bromine, iodine, and so on. You don't need to know this. For example, if I had a salt sodium bromide, and if I put a more reactive halogen like fluorine, what happens is the bromine and fluorine almost switch around. So the fluorine displaces or kicks out bromine from its bond with sodium, the Na, so it becomes NaF, so sodium fluoride plus just bromine on its own. And remember that the halogens are also diatomic molecules, so we found them naturally in 2 molecules of 2, and we'll need to balance this equation, which I'll do quickly. Next are the noble gases. Their common properties and trends, there's not many of them. First, the atoms here are stable. They already have a full outer shell of electrons. For example, it's full for helium. It has 2, or the maximum number for the first shell, and then 8 for the others. And that means, since they don't need to lose or gain any electrons, they won't react easily with other elements. The last property you need to know is that their boiling points increase as you go down the group. That's Unit 1 done. Now we move on to Unit 2, bonding and properties. and we look at three things: bonding types, properties due to bonding, and carbon structures. First, we look at bonding itself. Atoms need to bond with others to become stable, as I've said just previously, and they become stable when they have a full outer shell of electrons. And they can happen in a variety of ways. I've already said they can lose electrons or gain electrons, but sometimes they can share electrons. First, before we need to understand ionic bonding, we need to look at ions. So the ionic bonding is a way to transfer electrons or lose or gain them. Now remember, usually atoms have no overall charge, a charge of 0. So the same number of protons and electrons. On the last slide, electrons can be gained or lost to make it stable because they'll then have a full outer shell. Now, if any number of electrons are gained or lost, the number of electrons and protons aren't the same anymore. So the atom becomes charged and it becomes an ion. An example can be an atom of magnesium. So it has 12 protons and 12 electrons configured in this way. So 2 in the first shell, 8 in the second shell. In its outer shell, the third one, there's 2. Now, there's going to be a diagram as well. As you can see, the outer 2 electrons have been lost in some sort of reaction. They would then be picked up by another element. And now, since magnesium has a full outer shell, it's stable. However, it's now got 10 electrons and 12 protons. We know that protons are positively charged. So for every proton, it's 1 plus. So we have from the protons 12 plus. And each electron has a charge of 1 minus, and there's 10 of them, so there's 10 minus. So overall, when we add these charges together, positive 12 and a negative 10, you get an overall charge of 2 plus. There's 2 more protons than electrons. And remember, you write charges first with the number, then the sign. And remember that the ion has brackets around it, square ones, and its charge on the top right. Now, this can be also written as an ionic equation, which you may need to learn for some tiers. And this shows the electron transfer. So initially on the left, we have a normal atom of magnesium. Then it becomes an ion with a 2 plus charge. And as a result, there were 2 electrons lost from it. Now, we move on to ionic bonding now that we've understood how ions work. So describe, in terms of electrons, what is happening in this reaction between magnesium and oxygen. 4 marks. Electrons from the outer shell are only shown as crosses. Try this yourself. Now we'll go through the answers. Now, how this question commonly is marked is you talk about each atom, how it starts or reacts, and then what ion it becomes. So the first mark, we'll talk about magnesium. So magnesium loses 2 electrons from its outer shell, and you can say it loses them to 1 oxygen atom, and you can say why it loses those 2 electrons. So you can say to become stable or to gain a full outer shell for the same reason. That gets you a mark. The second mark comes from saying what ion magnesium turns into. So the magnesium atom becomes an ion with a 2 plus charge. It lost those 2 electrons, it lost a negative charge, so it becomes positive. Oxygen the atom gains 2 electrons from one magnesium atom, again for the same reason, to gain a full outer shell or to become stable. That's the third mark. And finally, the oxygen atom becomes an ion with a 2 minus charge. Next, you'll need to learn about covalent bonding. Some atoms instead share pairs of electrons, so instead they both contribute to each other and they add to their total to achieve a full outer shell. So this is covalent bonding, and this often occurs with multiple non-metal atoms. A common exam question could be to draw a dot and cross diagram showing how an atom of hydrogen covalently bonds with an atom of chlorine. Only draw electrons on the outer shells. Hydrogen is not in a group, but it only has 1 electron, so 1 electron in its outer shell. Fluorine is in group 7, so it has 7 electrons in its outer shell. Now that we know that, we'll draw our atoms in the middle. So for both atoms, you'll need to draw their elements, and then just 2 circles that just about overlap each other. Hydrogen only has 1 electron and it needs to gain another one because first shell is 2 maximum, second is 8, third is 8, and so on. So hydrogen needs to gain 1 electron. So it puts its own electron in the middle and receives 1 from chlorine. And remember, you need to have like a little key so that a cross is the electrons from a hydrogen atom and the dots are the electrons from a chlorine atom. Chlorine has 7 electrons and it will need to gain 1, which comes from hydrogen. And we'll put the rest of the electrons not in this intersection. So this intersection shows the shared electrons. So we need to fill in 6 more electrons because chlorine has 7 electrons in its outer shell. So put them around here. Next, we need to also draw covalent bonds in a simpler way. So there are alternative forms. For example, we use the oxygen molecule, O2. So each oxygen molecule or atom needs to gain 2 electrons because group 6 so has 6 electrons in outer shell. So 2 to gain. So we get a double bond, so 2 pairs of electrons shared. One alternative way you can show this molecule is through a ball and stick diagram. So if each atom is a ball, and each pair of electrons shared is a stick, so covalent bond. We'd show this with first a ball, which we'll write with an O, another ball with an O, and we'll draw 2 sticks between them. Next is the structural diagrams or lines, which you'll see much more when you do other units such as organic chemistry. In this simply you draw the letters of each atom or like its element. So we have O, then O as well, so 2 oxygen atoms, and we simply draw the bonds as lines, like this. So we'll draw a line from one atom to another and another. So this is actually a double bond, as we've said. Next, we look at metallic bonding. So if we look at pure metals, the atoms will be arranged in regular rows, like this. And we don't need to know the properties just yet. We'll see how metals have their own properties. So this entire section now is about properties of each type of compound. So we start with ionic compounds, the ones that transferred electrons from a metal and a non-metal. You'll need to be familiar with its structure called the ionic lattice. So these are also regular rows of ions this time. For example, we'll draw the lattice of sodium chloride, so Na atoms or ions, and Cl ions. We'll model them with different colored balls or spheres. So we'll draw Nas as red and chlorines as green. Just to draw a small section of the lattice, we'll have positive ion here, I will draw the bonds between them, so each electron transferred. So bonds here, here, here. What you get is this lattice, so it's kind of like a rectangular structure. Now we can see three things about this. So we have high melting points. These ionic compounds or lattices don't conduct electricity, and this unless, which I'll explain in a bit, and they are brittle. And you'll need to explain all three. They have high melting points because you have your two oppositely charged ions. So first we have sodium, which is a positively charged ion. And then we have chlorine, which is a negatively charged ion. Now, when you have ions that or anything that's charged with opposite charges, there is an attraction force, and we call this an electrostatic force of attraction. Now, since these forces are actually quite strong because they're charges and they're quite close together as well, this means we need lots of energy to break or overcome. This means they needed a high temperature, and therefore that's why they have high melting points. This also means that they are usually solid at room temperature. They don't conduct electricity because to conduct electricity, ions have to move. However, they can conduct electricity when molten, so that's when they're melted and the ions are free to move, or in aqueous solution, so that's when it's dissolved in water. And for both of these, you can just say ions can move. Lastly, they're brittle because they have these alternating layers of positive and negative ions. And as soon as we dislodge one of them, we have two ions that have the same charge, that they repel each other, and then they break apart. Next, we have small covalent molecules, and we'll need to know about intermolecular forces. So let's say we have molecules of hydrogen, so H2. And I'll draw the very simple diagram, which is just two hydrogen atoms, and they share a single covalent bond, so a single line. So if I draw many of these, these molecules can actually move around easily because they're so small, but they're only bound by these weak intermolecular forces. Therefore, they have low boiling points, and are liquids and gases at room temperature, and they don't conduct electricity. So first, we only need to overcome these weak intermolecular forces for all these small molecules to move around quickly. We don't need to break the covalent bonds. And they don't conduct electricity because there are no ions in this, and even though they can move around, they don't have a charge at all, and they won't conduct a charge through its structure. And a note of this is something called bulk properties, which is possibly a triple-only term. All these properties involve like many of these molecules. So it doesn't make sense to say, for example, the boiling point of a single atom. Next, we'll need to learn about giant covalent structures. One example is diamond. Now, these are carbon atoms. These are bonded in a tetrahedral shape, so like a pyramid. And the thing with diamond is that each carbon atom is bonded to covalently bonded to four others. So if I draw a diagram, like this. This will almost repeat itself. Now, it has a high melting point because there are little or no weak intermolecular forces. So instead, we need to break these strong covalent bonds, which require lots of energy. Next, we have properties of metals. Now, we've got another diagram of a pure metal. So we have regular rows, like this. I'll just draw 2 rows for now. Now, the thing you need to know about metals is that this outer shell electron, it might have, let's say, 1 per atom, that can actually leave the atom and float around and it becomes delocalized. So we've got random little dots here. These are delocalized electrons. They can just move around wherever they like. They can go to another atom. They can go back to the same atom. It's just random. And what we get is what the scientists call a sea of delocalized electrons. Now, since each atom has actually lost its delocalized electron, it becomes an ion. Now, this can explain 2 properties. So metals will tend to have a high melting point, and it will conduct electricity very well. Now, it has a high melting point because you have electrostatic force of attraction. Between electrons and the positively charged ion. So these are strong. And like I've said, they need lots of energy to overcome. And it can conduct electricity well because electrons are charged. They can move. Because they're delocalized. And therefore carry a charge through its structure. For triple, you'll need to know about a few structural properties. Now, we have pure metals versus alloys. We can represent these same diagrams again. So first, with the pure metals, you all have the same atom lined up in regular rows like this. Now, these are softer because they can be bent more easily because these layers can slide easily. Whereas alloys will have atoms of different sizes. For example, with steel, you'll have iron atoms and carbon atoms. So if I draw a few of these ones, now I draw a few small ones dotted around. So layers are disrupted, harder to slide and bend. So this is why many alloys like steel are much actually stronger and more useful compared to just the pure metals or like iron. Next, you'll need to know about diamond and graphite. We already know for both of them, since they are both giant carbon or covalent structures, they have a high melting point. So first for diamond, we remember each carbon atom is bonded to four others. So for example, if I draw a little structural diagram, and these bonds will just carry on forever like this. It will form this little tetrahedral shape. We already know it's a high melting point, and they are harder because, well, all the atoms are covalently bonded together. There's no weak intermolecular forces, they're not in layers. Therefore, they're harder to slide. Another point you need to know is that they can't conduct electricity. So this is because there's nothing that moves, because they're all covalently bonded together. So there's no delocalized electrons because each one is shared with another atom. And a good point to know is that carbon is in group 4, has 4 electrons in outer shell, needs to gain another 4 to become stable. Whereas graphite is a bit stranger. Each carbon atom instead is covalently bonded still, instead to 3 others. So if I draw out these structural diagrams again, you'll only have 3 bonds coming out this time. And if I draw this for several of these carbon atoms, what you'll then see is you've got hexagonal patterns. Like diamond, it also has a high melting point because you've got many of these covalent bonds to break, which require lots of energy. However, these carbon atoms are in layers in these hexagonal patterns with weak intermolecular forces. Meaning they can slide easily. Lastly, they can conduct electricity because one electron per atom is not bonded with another and it's delocalized and free to move. Even still, for combined and triple science, you'll need to know about graphene and fullerenes. Now, these are also giant carbon structures. Now we've got a few, and they have uses such as for electronics and structural support. And one of them is Buckminster fullerene. So there's 60 carbon atoms, all arranged in a sphere with various shapes. These are like pentagons and hexagons, so this it's almost like how a football is woven together. Lastly, you have nanotubes, which are also like a graphite, but instead are just tubes. And these uses, for example, have drug delivery and structural support as well. Now, we are in the next unit, quantitative chemistry, with 15 minutes in. And as an overview, you'll need to know about moles, Avogadro's constant, and for higher, on both combined and triple science, you'll need to know about reacting masses, limiting equations, balancing equations with moles, and concentration. And as well, for triple, you'll need to know about atom economy, and then percentage yield. But these two formulas are actually quite simple anyway. I could do them in another video. First, we learn the basics of quantitative chemistry. For all groups and tiers, you need to know about the conservation of mass, balancing equations, relative mass, and concentration. We get the relative mass of an element by comparing its mass to an atom of carbon-12, and this is just a fact you need to know. Now, if there are a certain number of atoms or molecules of that substance, its relative mass is the same as its mass in grams. So, for example, if we have one, that becomes 1 mole of the substance. So, like 1 mole of carbon-12. So, like a carbon atoms with masses of 12. This becomes simply 12 grams. And we get a few formulas. 1 is the number of moles equals its mass divided by its MR. So its mass number and lastly, we have the number of molecules is the number of moles times Avogadro's constant. Now, Avogadro's constant is simply just a number, a very special one. So this is where you'll need that many of that atom or substance to make the same mass of it as its formula or relative mass in grams. So that's 6.2 times 10 to the 23 molecules. So this will make up 1 mole of a substance where its mass number, like the atom or compound, equals its mass in grams. That's just a mole. So we can actually calculate the number of moles of a substance by taking its mass and dividing by its MR. So for example, if we've got 14 grams of lithium and we need to know how many moles there are, so we do 14, that's the mass of the sample, divided by its MR, or its relative mass, and you get 2 moles. Remember, the Li, Mr of Li, or it's the mass of the lithium atom, is 7. Now, moles can tell us stuff in equations. So the number before the chemical equations can tell us the number of moles of reactants that react together fully. So if you remember, in a reaction, the mass of reactants is the same as the mass of products. Nothing gets destroyed or created. That's the law of conservation of mass. For example, we get this equation here. So we have two atoms of magnesium that react together with one atom of oxygen, and that forms two molecules of magnesium oxide. So if we do a little count on each side, so we have 2 times the single magnesium, so we have 2 magnesium on the left. We also have 2 magnesium on the right, because this 2 counts to this whole thing. We have a single diatomic molecule of oxygen, so there's 2 oxygen atoms in there. And also on the right, we've got 2 oxygen atoms, because in each magnesium oxide there's 1 oxygen, and since we have 2 of those molecules, we'll have 2 oxygen. So the number of each atom is the same on each side, so nothing's been gained or lost. So therefore this equation tells us 2 moles of magnesium react fully with 1 mole of oxygen. So for every 2 moles of magnesium we need at least 1 mole of oxygen to react with it. And this forms 2 moles of magnesium oxide. And you'll need to see these things called mole ratios. And you can scale this up or scale this down. You can scale up to a big reaction, for example, where 4 moles of magnesium could react with 2 moles of oxygen. You could scale it down maybe to 0.2 moles of magnesium reacts with 0.1 moles of oxygen. Now, the first bit of higher tier is using moles to balance equations. So first, we've got this 22.4 grams of iron fully reacts with 29.2 grams of hydrochloric acid to produce 50.8 grams of iron chloride and 0.8 grams of hydrogen. And we've got an incomplete, unbalanced equation here. You're also kindly given the masses of each atom, but you'll need to find the formula's mass. So you add up all the masses of each atom in the compound. So I'd put all this information into a little table. Right, here we are. So we've got each chemical, and we've got its mass, and we need to find the MR of each of them. If it's just a single atom like iron, it's very simple. We just have it on its own, so Fe, one atom of Fe, that has a mass of 56. HCl, so you have one atom of hydrogen and one atom of chlorine. So together it's 1 plus 35.5, so we get 36.5. Next we get iron chloride, we're given the formula for that. So we have one atom of iron and then 2 atoms, so this little 2 here. So we have 2 atoms of chlorine. So that is 56 plus 2 times 35.5, and this gets us 127. And then for hydrogen, we have 2 atoms of hydrogen. So that's 1 times 2, and that's simply a mass of 2. Now we need to find the number of moles of each substance. And to remember the formula, moles equals the mass of the sample divided by its MR. So that's its formula mass or atomic mass. So for the example, for the first one, we have 22.4 divided by 56. This gets us 0.4, so 0.4 moles. For the second one, hydrochloric acid, it's 29.2 divided by 36.5. This gets us 0.8. For the next one, iron chloride, we have 50.8. Divided by its mass, or its relative formula mass. This also gets us 0.4 moles. Lastly, we have hydrogen, that's 0.8 grams divided by its formula mass, which is 2. This gets us 0.4 moles. Basically, we need to then multiply all of these to get whole numbers. What we can do is divide by the smallest, so the last step. So if we divide everything by 0.4, we get this. So we have 1 mole of iron. Then we get 2 moles of hydrochloric acid, 1 mole of iron chloride, and finally 1 mole of hydrogen gas. So if we rewrite the equation with it balanced, so we can see that we don't need to put a number of it's a 1. So for every mole of iron, we need 2 moles of hydrochloric acid. So we put the 2 in front of the HCl. This reacts to form just a mole of iron chloride. So if we leave it as it is, and just 1 mole of hydrogen, so just H2 on its own. Next we have reacting masses. So we'll be given an equation that's this time balanced. For example, 9.45 grams of aluminium reacts with an excess of oxygen, so that's more oxygen than you need. So you can just ignore this basically to form aluminium oxide. So how much aluminium oxide is made? 4 marks. And we're given the ARs of each atom. First, we need to organize the information again. Here's the equation. Now we've got a little shortcut as well. I've rewrote the question. Now, what I do is write the mass of each reactant or product above it. So we have 9.45 grams. We can ignore oxygen because this is an excess. And then we need to find out how much aluminium oxide is made. So that's the mass we want. We put a question mark here. Now we need to find the MRs of each. So we have 4Al. And it helps probably to put brackets around the whole compound. If we don't have anything between the brackets, we're just multiplying. So we have 4 times the AR of aluminium, which is 27. So we have 4 atoms of aluminium. That turns out to be 108. If we have 2 atoms of aluminium oxide, we have each aluminium oxide atom is 102. So that's 204. Now the shortcut is we have the mass of known product, or the one we know, so that this can be a reactant or a product, divided by its MR of known times by the MR. So to put numbers in, so we have the mass of our known chemical, so that's our aluminium, so that's 9.45 grams. We divide this by the MR of our known chemical, so that's divided by 108. Then we multiply this by the MR of the chemical we need, so this is one we need. That's the aluminium oxide, and that has an MR including the number of 204. As a big note, include the numbers here. When you put this into my calculator, we get a nice number of 17.85 grams. Next, we need to know about limiting reactants. So we need to know a few things. If something is in excess, there's too much of it, so there's more than we need in the reaction. Whereas the limiting reactant is the opposite. So this reactant runs out first. And basically it limits the reaction because once any of the reactants run out, the reaction stops. So it stops it from happening any further. And we'll use the example from the previous question. For example, we had an excess of oxygen. So there's too much. So that when the reaction finishes, it's left over. Now we'll use another example. 9.54 grams of copper oxide reacts with 2.64 grams of carbon. Show that copper oxide is the limiting reactant. 4 marks. Now as a big note, for some reason in this calculation you need to ignore the numbers. But there's none here anyway, so any of the large numbers. So we know there's 9.54 grams of copper oxide. And we got 2.64 grams of carbon. And we can just ignore the rest of these because they're irrelevant. Now, the first step is to calculate the number of moles. First, we'll calculate the MR of each. You get 79.5 here, whereas carbon is just 12. So when we divide, we get the number of moles. We get 0.12 moles for the copper oxide. For the second mole, we get 0.22 moles of carbon. The second step after this is to use the mole ratio. So when there's nothing before the chemicals, we can just put a 1 there to make things easier. So we know from this 1 mole of copper oxide reacts fully with 1 mole of carbon. And we can say this one way or the other. For example, if we plug this in, for every 0.12 moles of copper oxide, it needs 0.12 moles of carbon. However, what we can see from our calculation is 22 moles is larger than 0.12. So therefore, we have too much carbon. So carbon in excess. Therefore, the other chemical is the limiting reactant. Because this will run out first. And that's mainly it for the combined and a bit of triple with the quantitative chemistry. Now we have an overview for topic 4, which is the reactivity series, reactants with acids, electrolysis, and a few required practicals. Now first, we need to know about oxidation reaction and reduction as well. So metals can react with oxygen to form metal oxides. So with oxidation is where oxygen is gained. So a metal reacts with oxygen to form a metal oxide, and reduction is where oxygen is lost instead. It is possible sometimes for some metal oxides to react with something else, like carbon, to get just the metal. Metals can also react with other nonmetals other than oxygen, for example, chlorine, fluorine, sulfur. This time, oxidation is where an atom loses electrons, and reduction is where an atom gains electrons. And if you remember, you can use the keywords oil rig. So oxidation is lost, and reduction is gain. Next, you'll need to know about the reactivity series. Now, a few things you need to know is that this is the most reactive at the top to the least reactive at the bottom. Now, if something is more reactive, it can do a few things. For example, with carbon, metals less reactive than carbon can be displaced. A good example can be copper oxide. What happens is the carbon displaces the copper because it's more reactive, so it basically kicks it away and bonds with oxygen. So what you get is just copper on its own, the less reactive metal or element, and then carbon bonded to oxygen, so that's just CO. Whereas let's say all the metals more reactive than carbon have to be obtained by electrolysis. Next, what you need to know is that metals more reactive than hydrogen react in acids, whereas these ones can't react in acids. I'd like you to take a screenshot of this as well, because this is information everyone needs to know. Next, you'll need to know what an acid is. Now, all acids contain H plus ions, so this is basically a hydrogen atom just without an electron in its outer shell, so it's empty. And these often bond to the negative ions made up of other nonmetals. So you need to know about three acids first. So you've got hydrochloric, so you've got in hydrochloric acid, you've got hydrogen and chlorine, and we know the hydrogen is positively charged, so to balance it out, the chlorine is negatively charged. In sulfuric acid, you'll have two hydrogen ions, so we have in the because we've got two hydrogen atoms here, and to balance out the SO4, the sulfate ion, is 2 minus. And lastly, you may need to know about nitric acid. So we've got one hydrogen atom here, so we have one H plus ion, and we have a I think a nitrate ion. Now the pH scale measures how acidic or basic, so this is an opposite of an acid, a substance is. So its range starts at 1 and goes up to 14. So acids tend to have a low pH, like 3, whereas bases tend to have a high pH, like 10. Now bases and alkalis are very similar. Alkalis are a type of base. These are just soluble. Now, last thing you need to know is a pH of 7 is considered neutral, and a good example of a neutral liquid is just water. Now, the scale also tells us how many H plus ions there are. Now, if we increase the pH by 1, like from 1 to 2, the number of H plus ions decrease by a factor of 10. So it divides by 10. So it gets less acidic as the pH increases. So, for example, if the pH goes from 2 to 5, that goes up by 3. But the number of H plus ions, it decreases by 10 3 times. So it's decreased by a factor of 1,000, or just 10 to the power of 3. Now, a common exam question can be if an acid is strong or concentrated. So these are two ways to describe an acid. So a strong or weak acid depends on how it ionizes within water. So when ionizes, it splits into the H plus ion and the negative ion. For example, a strong acid could be hydrochloric. And if you remember, it had two ions, a H plus ion and a Cl minus ion. Now, if it's strong, it ionizes completely. In other words, it just splits. Whereas weak acids, for example, I'll use um, ethiotic acid. These won't ionize completely. And then ethiotic acids. So this means the ethanoic acid can split into its ions, but those ions can join together again to form the original molecule. So most of the time, not all of the ethanoic acid is split into ions. Lastly, if it's concentrated or dilute. So this tells us how much of the acid there is per unit of volume. For example, think about how salty some solutions can be. And usually you'll have the acid measured in moles, and then per unit of volume is usually cubic decimeters. Next, we have neutralization, where an acid or base or an alkali react together to form two things, a salt and water. Now, the general equation is an acid and base forms a salt and water. Now, the two reactions have different pHs and will neutralize each other. Now, the pH now is actually 7 because it's neutral and we produce water. Now, the salt is the hardest part of the equation because you'll be given the acid and the base and you'll be asked often to name the salt. Acids contain hydrogen and a negative ion, whereas bases contain a metal and oxygen or a negative ion. This is usually something like OH minus. Now what happens is the water is formed by the H plus ion and this forms water, while the metal from the base goes with the negative ion, that's from the acid. This forms the salt. For example, sulfuric acid and sodium hydroxide form sodium sulfate. Some of the acids, we had the negative ion, which was a sulfate ion, whereas the metal came from the base, and this base had sodium, so Na. Now, Na is in group 1, it loses 1 electron, becomes a 1 plus charged ion. And then the sulfuric acid, or the sulfur ion, has a 2 minus charge. And to name the salt, you put the two together, and what you do is you swap the numbers around. What you get is the 2 here, and the on the left, and the 1 on the right. So we have 2 sodium ions, or 2 sodium atoms, and then just 1 sulfur ion, or sulfide ion, or sulfate. Next, you'll need to know about the reaction between acids and metals. So we have a general equation again. A salt is also produced, and naming the salt is the same as neutralization. So we have the metal just itself, which is easier, and then the negative ion from the acid. For example, we could react magnesium and then nitric acid. This will form a salt plus hydrogen gas. Now the salt gets its metal, it's magnesium, and the negative ion comes from the acid, nitric, so nitrate. If you're interested in the formulas, you'll have Mg plus HNO3. Now Mg is a 2 plus ion, NO3 is a 1 minus ion. So if we switch them around, The salt has a formula of just one magnesium ion and then two nitrate ions. So we have the brackets around the NO3 so to represent it's just that batch. That was a two. So two of these nitrate ions. That's our formula. Hydrogen always exists as a diatomic molecule like H2, unless it's an ion. And then we balance the equation. Now, a required practical is making a pure, dry set of crystals from a salt. Now, that's actually for all groups and tiers, so all of you need to pay attention. This often comes up as a 6-mark high mark question. For example, we'll use an appropriate acid and base to make the salt we want. For example, iron chloride. And if we remember the metal from the base, and then the non-metal from acid. Now, before we start the general method, we'll need to identify the chemicals that we need. So the metal comes from the base, and usually we want to use an insoluble base. This can be either an oxide or carbonate, and you'll see why. So for example, the iron is the metal, so iron oxide will be our base. And the non metal from the acid is chlorine, so chloride, so Cl, that has a 1 minus charge, and that comes from hydrochloric acid. Now we have a general method, so we'll warm a set volume of acid in a boiling tube, and that's going to be submerged in, let's say, a beaker of hot or warm water. You can use any volume you like, but you need to be sensible. I wouldn't go above, let's say, 40 cubic centimeters, otherwise it's too much. Now you need to add small amounts of the insoluble metal oxide or the metal carbonate with a spatula, and you need to stir with another rod so you don't contaminate anything. And you add it until an excess. This means when you add it, some still remains. And it's easy to tell because within the soluble base, it will not dissolve, and if it hasn't reacted anymore, it won't disappear and it'll just stay there. Now, we don't actually want this metal oxide anymore, and we need to filter it out because it's insoluble, so we'll use filtration. So we need to filter out this excess metal oxide using a funnel and filter paper, and we collect the solution into an evaporating dish. So draw a simple diagram, this is our funnel, and we've got filter paper, and we pour it in, and then just below we'll have an evaporating dish. We'll just collect just all the liquid that will have the salt dissolved inside it. Next, we heat the evaporating dish until most, not all, of the water evaporates. Most of the water. Then we turn off the source of heat and we place the evaporating dish near a window instead. And this is so we get crystals, not a powder. Lastly, you'll need to filter out the crystals because not all the liquid will evaporate. So you'll need to filter them out, again using a funnel and a filter paper. and then you'll use another piece of filter paper or just a wet paper, a dry paper towel to pat the crystals dry, because you remember you have a pure salt because it's just in solution, and you want dry crystals. The next topic, or actually practical, comes from triple science, and this is titrations. So what you need is an acid and an alkali, one with a known concentration and the other unknown, because the point of a titration is to find the concentration of an unknown acid or base alkali. Like, let's say you've got a new bottle of acid, but it doesn't tell you what concentration it is, and you can use a titration to find it out. You'll just need to know the other reactant and its concentration. Some other equipment you may need is a conical flask, a one-sided indicator. So rather than using, don't use the universal indicator. Some other examples could be, for example, we'll say the colors when it's an acid or base or alkali. For example, we have litmus, which is often paper. This is red when it's an acid, and then blue when an alkali. Another you could use from the top of my head is methyl orange, which was yellow as an alkali, and then it turns red as an acid. Those are the two indicators you could use. And the good thing about this is it almost instantly changes color. What you'll next need is a burette. So this is a tall tube. You'll have your tap that controls the flow, and it just drips out. And you'll have scales on top to see how much acid you've used as well. Something else you could use is a white tile, so you can easily see a color change. And lastly, a funnel. That's when you're pouring the acid into the burette. Now, the titration method is this. So the task is to find a concentration of an acid based on how much of an alkali is needed to neutralize it. So what we'd first do is we fill the burette with the alkali to the top using a funnel. And a bit of precaution is bring the burette down. Don't fill above eye level. This is for safety measures, and you usually have safety goggles on already. And usually this is just to minimize the risk of you pouring any chemicals, alkali or acid, onto your eye by accident. Next, you measure a set volume of the acid into the conical flask or the chemical you want to find the concentration of. And then you add a few drops of your indicator. This case, I'm using litmus because it's familiar with many people. Next, you'll place a white tile underneath the burette and then place the conical flask on top of the tile. Next, whilst continually swirling the flask. Open the tap on the burette to let the alkali fall into the flask, which neutralizes the acid. So at first, you'll see that the solution is blue because it's alkali. But when it becomes neutral, it's no longer an alkali and it starts to see some red. So that's the color change you look for when you use litmus from alkali to acid. Now when most of the litmus solution changes color because you're swirling it, you tighten the tap, letting it flow drop by drop so you get the exact measurement. And then you shut the tap when all the solution has changed color and you record the volume of alkali that neutralized the acid. And then you repeat these steps again to get a total of 5 volumes that neutralize the acid because it may vary each time. And it's a random error because you may shut off the tap at different times when you judge when the reaction is finished, like when the color change is fully done. Now, a bit of maths involved here. We're finding the unknown concentration of a sample of hydrochloric acid based on the volume of sodium hydroxide needed to neutralize it, along with us knowing its concentration. And we've got the equation here. There's a few steps involved here. First, you need to find number of moles of the known chemical. You find a number of moles. This is the sodium hydroxide. Then you'll use the mole ratio. And lastly, you'll find the concentration. Now, concentration tells us how much of a substance there is per unit of volume. So that is number of moles divided by its volume, which is often in cubic decimeters. And remember, this is basically just 1 liter. So 1,000 cubic centimeters is equal to 1 decimeter cubed. So part 1, we calculate the number of moles. And what we do here is 0.4 times the volume, since we rearrange the equation. Number of moles is the concentration times the volume. So this gives us the number of moles, 0.013. So we use the mole ratio. So we see that for every mole of hydrochloric acid, we need a mole of sodium hydroxide to neutralize it. So that means they have the same number of moles in each. So the same number of moles of acids and the same number of moles of alkali. So that was 0.013 moles of hydrochloric acid. And lastly, we calculate the concentration, which is the number of moles divided by the volume. And remember to convert your cubic centimeters to cubic decimeters. In other words, in liters. And lastly, you get a concentration of 0.52 moles per cubic decimeter. Next, you'll need to know about electrolysis. Now, as a recap to bonding, how can ionic compounds conduct electricity? If you remember, they have to be either molten or an aqueous solution. And a crossover with physics is, what charge does current flow from and finish? So what polarity, positive or negative? So it flows from positive to negative. And remember that opposite charges attract. Now, we first need to learn about electrolysis with molten ionic compounds. An industrial example would be extracting aluminium from aluminium oxide. So that'll be Al2O3. Now, what are the ions in aluminium oxide? So we have aluminium, and aluminium tends to lose electrons and become positively charged. So if you look at the group it's in, so Al is group 3, so loses 3 electrons. So we have a 3 plus charge. And then with oxygen, it's in group 6, so it needs to gain 2 electrons to get the full 8 and have a full outer shell. So we have 2 minus here. Now, there's a bit of side information. Something called cryolite is added. And this lowers the melting point of the aluminium oxide. And if we lower the melting point, we need less energy to melt, and therefore it's cheaper. Now what actually happens is you'll have a big container of this molten stuff, and you'll have 2 electrodes. One is positive, and the other one is negative. So we have our molten solution, and we've got different ions. So we've got positive aluminium ions, and then we have negatively charged oxygen ions. And remember that opposite charges attract. Now what happens is this aluminium ions then gets attracted to this negative electrode called a cathode. This gets electrons, so it gets 3 electrons for each atom and just becomes aluminium. So this starts to get a nice coat of aluminium. Whereas on the other side, oxygen gets attracted to the anode and just becomes oxygen and leaves 2 electrons. That just gets released. However, these cathodes and anodes tend to be made up of graphite, which is made up of carbon. Now these need to be replaced often because they react with the oxygen produced. They get oxidized to produce carbon dioxide. So actually, at the anode, we do get non-metal produced, or the OH ion, it gets to the electrode. So we get either oxygen ion instead. So you will just get the metal or hydrogen gas if the metal is more reactive than hydrogen. Now, as a bit of practice, try and identify what gets made at each electrode. If I have, let's say, um, iron chloride, sodium chloride, if it's present. Chloride is chlorine, which is a halogen, so that gets produced. So we have chlorine gas. At the negative electrode, or the cathode, we either get the metal produced, or hydrogen gas if the metal is more reactive than hydrogen. So in this case, iron is more reactive than hydrogen, so hydrogen gets produced. Now with sodium chloride, we look at the anode. Now we get non-metal produced, or the oxygen, or halogen if it's present. Chloride is chlorine, so that's a halogen, and that gets produced, so we have chlorine gas. Whereas the negative electrodes, or the cathodes, we either get the metal produced, or hydrogen gas if the metal is more reactive than hydrogen. Sodium is clearly more reactive than hydrogen, because it reacts with acids and water and all sorts, so we just get hydrogen gas produced. Next we have magnesium sulfate, where at the anodes we have oxygen, or if a halogen is present. Sulfate ions are not halogens, so we just get oxygen at the anode. And at the negative electrode, or the cathode, magnesium is more reactive than hydrogen, so hydrogen gas is produced. And some useful path equations or ionic equations you may need to know are for the oxygen. Is this, which is a lot to learn, whereas at the negative electrode for hydrogen being produced, you will have your H plus ions that gain an electron and become hydrogen gas, which is H2, but we need to balance. Well, the halogen half equation could be chlorine, for example. So chlorine is a negative ion, and that will gain some electrons. It will become chlorine gas, so chlorine, but it exists as a diatomic molecule, so we'll have to balance everything out. With the final unit, it's its energy changes. So an overview, you'll need to know about endothermic and exothermic reactions, some reaction profiles, factors affecting the temperature change, and energy changes calculations. So what happens in a chemical reaction? So let's say we have a very simple reaction, like hydrogen and oxygen. These react to form water. All three of these are actually covalently bonded molecules. So let's say we'll have H2, we'll balance quickly. As you can see, the atoms rearrange. For that to happen, two things need to happen before this works. So reactants, bonds must be broken so they can move about and then they can rearrange themselves. And then products bonds must be made. And that finishes the reaction. Now to break bonds, you need energy to put in them. So energy in, whereas if you make the bonds, energy is released. Next is an exothermic reaction. So we need to know what's meant by an exothermic reaction. So an exothermic reaction transfers. And they like you to use that word, transfer. So it transfers energy, like thermal, to the surroundings. And if we go back and see what happens in a reaction, since energy overall is transferred to the surroundings, so it's released, so less energy is needed to break bonds, whereas more energy is released, forming bonds. And a few examples of these exothermic reactions or any uses, one could be combustion, another could be hand warmers, those are two, for example. Next, you'll need to know about endothermic reactions. Now, what's meant by an endothermic reaction? It's the opposite. So energy, so it takes in or absorbs or transfers again energy from surroundings. Now this time, since energy is overall absorbed or taken in, so more energy is needed to break the bonds. Less energy released from forming bonds. And some common examples could be ice packs and decomposing materials. One I could think of is decomposing copper carbonate. This is actually one step with producing copper. Now you'll need to know about reaction profiles. So we have a few things we'll need to label. So an example I'll do is for an exothermic one. Now first you'll have two horizontal lines which represent your reactants and products. Label your reactors first. So these is your reactant line. Now the curve will actually go up first and down to the product line. Now, if we draw a dotted line, this little height here was the energy needed to break the bonds. Because that is activation energy. Whereas this, from the height of this curve down to the product line, is the energy released. From forming bonds. And then this little line here from the reactant to product line is just the overall energy change. And you may see some past papers label this as delta H, or enthalpy change. These all mean the same things. Now, the one for an endothermic is slightly different, but still similar. So we'll have the same axes. Energy on the vertical axis, and then progress of reaction or time on the x-axis. This time, we need energy to be absorbed, so the chemical energy store of the chemicals increase, so the reactant line is actually lower. It still rises up, but reaches here. So this massive upward arrow is the activation energy. So that's the energy needed to break the bonds, whereas this is the energy released going down. If we draw a dotted line across, we can see this gap between the reactant and product line going up is the overall energy change. I suggest you take a screenshot of this as well, because this has always been on many papers. One of the final bits of this unit is the energy change calculation. So propane combusts with oxygen, so reacts with oxygen to form carbon dioxide and water. Now use information below to calculate the overall energy change of this reaction. Energy is measured in kilojoules per mole. And we have these bond energies. Now I'll draw out the structures. C3. So we have propane, oxygen is this, CO2, water is this. Now remember we got one like this. Now highlight each of these bonds with a colour. CC bonds with this. CH bonds with this. Now first what I do is for the reactants is I'd list out all the bonds. So first I've got 2 CC bonds, as well as that we've got 8 CH bonds. And I just write the energy underneath. And also 5 O bonds. So the reactants bonds has a total energy of 6,475. So needed to break. Whereas the product, we'll list out the bonds here. So in each CO2 molecule, you'll have two C-double-O bonds. And since we've got three molecules, we got 3 times 2, so 6 of those bonds. As well as that, we've got the bonds from the water molecule. In each molecule of water, you'll have two OH bonds, where an oxygen atom is bonded to a hydrogen atom. Since we have 4 of these molecules, we'll have 8 of these bonds, so 8 OH bonds. If we calculate the energy, we got 6 times 799 plus 8 times 459. This gets us 8,466 kilojoules per mole. So this is released when forming bonds. Now, to find the overall energy change, it's the bonds broken. So the bond energy needed to break the bonds minus the energy needed to form bonds. Since it's an exothermic one, we'll get a negative number. So it's 6,475 minus 8,466. We get negative 1,991. That's an example. One of the last things is the required practical. And this is for all tiers and groups. So triple science, combined science as well, both higher and foundation. Now, the investigation is, to what extent does the temperature rise in a neutralization reaction? For example, this neutralization reaction is, as a note, exothermic. The method is, we add 25 cubic centimeters of a specific concentration of hydrochloric acid. When you add that to a polystyrene cup, and this is because we need to insulate this reaction so energy doesn't get lost to the surroundings, so basically our measurements are accurate. And we can do this by using a measuring cylinder to make sure it's 25 cubic centimeters. And what you could do is place this polystyrene cup in a beaker to make it stable so it doesn't rock around. Next, what you do is record the starting temperature of the acid with a thermometer, and then you'd add 5 cubic centimeters of sodium hydroxide into the cup, and you start stirring with a thermometer. And then you record the highest temperature reached, and this is when it stops rising. Then immediately record this, and then repeat steps 3 and 4 until a total of 40 cubic centimeters of sodium hydroxide has been added. So you'll keep adding basically the other chemical, sodium hydroxide, into 5 cubic centimeter like batches or increments, and you keep measuring the temperature after it. And what you'll get is just some strange results that aren't like any other practical. So on your x-axis, we'll have volume of sodium hydroxide, and then you'll have the temperature. increase. And don't forget the units on your axis. What you'll initially get is some crosses that go up. However, they either start to go down or flatten out a bit. And what you do is you have two lines of best fit, one for going up and one for going down. Now, initially it goes up because when you add the sodium hydroxide, it reacts. And when it reacts, it releases energy because it's an exothermic reactant, so the temperature keeps increasing. However, it stops increasing and starts to decrease because when you add it, it doesn't react this time because all of the acid has reacted by now. This means we're pretty much putting a cooler liquid into a warmer one. This is why it decreases. Now that's actually it for tonight. That is Chemistry Paper 1. I hope to see you soon. Goodbye from me.